Pre-calculus students, here we are in section 11.3. We're going to be talking about the number e. The number e is an irrational number, and so I put pi here because you'll remember that pi is also an irrational number. E is approximately equal to this value, and since it's irrational, you know I've got to use these wavy lines because I could never actually write out all the digits of e, but there are equations that we can use to explain what e is. E is going to be a really prominent value when we think about exponential growth and decay, so much so that we even think of it's going to affect how we consider logarithms as well. What we want to consider here is that when you are thinking about exponential growth and decay, you can use this type of a formula as well, where we have our initial amount is n naught, and then e times k to the t power, where k will be a given constant that refers to the decay or the growth of a particular bacteria or item or thing that we're talking about, and then t is just over time. So this is going to be a valuable equation that we'll talk about. I made this look really bad, so I'm going to try one more time again to write it like a human being. So here's what this looks like. You remember that when we talked about investing money in the last section, that we talked about compounding interest on a daily basis or on a basis that is n times. So it could be 4 times a year, 10 times a year, 365 times a year. We can compound interest, and we saw that that's where our formula got us. But if you were to kind of take this to the next level, if you were to think about compounding interest as n approaches infinity, this is the formula that we would get. That's how E will help us out in these problems here. We will be able to think of compounding continuously. So not just compounding daily, monthly, or by the minute, or even by the second, but literally every different time, every different moment in time, the interest will be slightly different. And this formula gives it to us. And so PERT is a quick way to remember it. A is equal to P times E to the RT power, where R is the rate and T is the time in years. So that's what we're going to work on as we go through these problems today. In this situation, we are dealing with the idea that at one time we would use DDT, which is a pesticide that would help kill off mosquitoes that transmit like diseases and lice and all these things. And it was pretty good and pretty effective, except it started posing health risks. So by January 1st, 1973, the United States Environmental Protection Agency banned all uses of DDT, and that 1.10 to the 10th power grams had been used in the United States. 1 times 10 to the 10th kilograms had been used in the United States before the ban. How much of that will remain in 2005, right? So this is kind of an interesting. Now, one thing I noticed is that they started it here with 1.0 times 10 to the 10th, and then they have 1.0 times 10 to the 9th, which is a factor of 10, which is pretty huge. So I'm not quite sure which is the reliable one, but we're going to solve this one just because it's the way the problem was written. So I'm not sure which one is the fact. Sorry for that. All right, so the first thing they want us to do is to write a function to model the amount of DDT remaining in the environment. So that's just in general. So we remember that we're going to use this amount. So our initial amount, y is going to equal our initial amount, which we're going to have as 1 times 10 to the 9th power in kilograms. And we're going to multiply that by E, remember that formula we just talked about, to the K, that's the factor of decay that we have with this particular substance. So e to the k times t. So I'm going to just leave t as t because the number of years could be whatever, depending on how long you are trying to measure this. So write a function to model the DDT remaining in the environment. So this is what you would use, where t is the value in years, and you can always solve that for y. Then they want us to find the amount of DDT that will be in the environment in 2005. Well, we have to think about the time lapse from 1973 to 2005. That's going to be 33 years. So this is what we'd have. 1.0 times 10 to the 9th times E. I didn't really get a 10 to the 9th in there. Here's what I'm actually going to do. 1 times 10 to the 9th is 10 to the 9th. You guys cool with that? So 10 to the 9th times E to the negative 0.02 11 times t, which is 32 years. You guys get the 32 years, as that is the amount of time that transpired between 1973 and 2005. So let's go ahead. We'll graph this after we get it. So let's continue with part B as we use our calculator to calculate the amount that we have. So we end up with 10 to the ninth times 0.509. These multiplication symbol and the points look kind of weird. My point in telling you this, though, is that really after 32 years, half of the DDT is still circulating in the population. I don't know after 32 years, but we've had some more years. We could have calculated it to 2021 and seen what value we got. And you can happily do that to see how much is left. So, but you see, the half-life, there's still quite a bit amount left. So next we're going to look at C, and we're going to graph the function using the graph to verify your answer in part B. And so to graph it, we're going to start off with this function here. We'll put it in Desmos, and then we'll see what happens when x, which we're going to use for t, is equal to 32. Okay, so we can kind of get an idea. I had to do a lot of adjustments to the x and y axis since I'm dealing with time. 0 to 100 years I thought was pretty good, so I got a little bit more than that. And then over here, remember we were dealing with 1 times 10 to the ninth, so 10 to the ninth is what I had my range for when I was dealing with my y-axis. So I did have it as 10 to the ninth. I don't know what they did here. They did 9 times 10 to the eighth, which is very close to 10 to the ninth. And so here's what we have. And so this is our graph, and we're using our graph to determine if what our answer said was correct. So at approximately 32 years, yep, it's about halfway gone. We've got about, well, no, actually it looks like a little bit more. It looks like that's 10 to the eighth times, yeah, this is the same thing. It is halfway gone because it went down to 10 to the eighth, but it's 5 points. So they're writing it in scientific notation as opposed to the 0.5. Y'all with me? Y'all know what I'm talking about. You're confused. All right. I hope this made sense. Let's go on to the next example. Hold on, guys. So this example is going to use the investment, the continual compounded interest invested. So they're asking us to compare after 25 years, $10,000 invested, earning 6.75% compounded continuously to the same investment compounded semi-annually. So the continuously compounded investment, we would use PERT. Okay, so the amount is going to equal to the principal times e to the RT power, whereas the compounded semi-annually, that means twice a year, right? So that means we're going to use the amount is equal to the principal times 1 plus the rate over 2 times 2 to the 2t power, okay? So let's see what our value is. So if we compound it continuously, constantly compounding this interest, dividing it up into smaller pieces and compounding it, this is what we get. The amount is equal to 10,000 times e to the 0.0675. So we write the decimal version of the percent, and we're going to keep it in the bank for 25 years. So we're going to get that answer, and at the same time, we'll calculate this guy. Again, $10,000. So 0.675 cut in half is going to be, what is 75 cut in half? Well, let me just write it all in here. 1 plus 6.75, and I'm going to write it as the decimal that I should. My bad. 675. All of that over 2. And that, again, is to the 50th power because I did 2 times 25. Y'all with me? Okay, let me go grab my calculator and I'll give us some answers. And even though 25 years is a pretty long time to leave money in the bank, we see that it definitely is the best choice to allow that money to be compounded continuously instead of at regular intervals. And I mean, the difference is not that great, but about a couple $1,000, almost a couple $1,000, $1,500 is pretty significant to most of us. So I think that would be a good investment indeed. So make sure you memorize these formulas and feel more comfortable using them. You don't have a whole lot of problems for this particular assignment, but make sure you try to get them all done because they're a little involved. Word problems, you know. All right, take care, guys. Look forward to talking to you soon. Bye-bye.